There we go. Now we're about ready to wrap up our chapter on 2D motion. So to summarize, it's been a bit like chapter 2, but with some extra applications and with multiple dimensions. And I think you can see that with multiple dimensions, we've obviously been able to expand the types of motion we've been able to talk about. So in addition to projectile motion, we were able to talk about circular motion, which we have right here, right? And if you recall what we said about circular motion yesterday, I was asked to go over the checkpoint again to make a few things clear after we ended. Let me make this bigger on my screen. Computer screens are always fascinating. So keep in mind that we have an acceleration because even though the speed is not changing, the velocity is changing. Okay, if the direction is changing constantly. So if either the speed or the direction is changing, you have an acceleration. And that can be counterintuitive because we're used to thinking of things in just purely terms of numbers. The direction, even though we can see it, it doesn't always resonate with us right away. And so that's one of the things we'll need to get used to as we solve these problems and get deeper into them. So as you can see, well, no, you can't see. Now you can see. As you can see from my pointer, the velocity vector will change even with the smallest change of the position on the circle, but the acceleration, even though it's changing rectangularly, radially it's always pointing towards the center of the circle. And this gets confusing because it's a hodgepodge way of describing things. If you pick any one point on the circle, usually you'll pick a rectangular coordinate system to describe everything, which is what we do in the checkpoint. However, you're sort of switching on two descriptions and it can seem inconsistent. So this is where you'll notice that understanding something or arriving at a conclusion really depends on interpreting the problem and not so much on turn the crank mathematics. So let's go back to the checkpoint really quickly. All right, it's a good place to review and to talk to get ourselves ready for the next chapter anyhow, because again, none of this stuff is disappearing. The skills we need to interpret, and it was specifically asked about vectors, we're going to need those skills going forward. So let's make a quick coordinate system and go over this again. So I'll just make my lines. I'll just do the best I can. I'm not going to be super worried, but, you know. And let's see, we want to make a ellipse circle. And that circle's good, but we want to move it here. That's okay. It's good enough. All right. So I'm going to use my pencil here. And we want to look at our points. So the initial point we look at here, right, if we make this into a if we only look at individual points in our XY coordinate system, we can see that our acceleration vector will point this way, right, if we're moving in circular motion. This is at x equals -2. If you look in the, if you look here, see -2. Find the point first. The velocity is at -4 meters per second. So let's pick another color. Tired. So the velocity will basically be going down. It's not perfect, but I think you get the idea. Now, you'll notice that the velocity that the velocity is given by -4 meters per second in the j hat direction. So this is a vector. Okay? So you could write here, if you want, that at this point, you can write that at this point here, we can write for the point we're looking at, we can write A is equal to v squared over r, which we already know will be 8 I hat. You'll notice that the acceleration is pointing in the positive direction in the x-axis. See, it just goes to the right. And we can tell from using our acceleration vector, because we always point towards the center of the circle, that that's where we go. Now that's for the given point, just the given point, okay? Well, that's, hold on, I'm gonna, okay. All right, so that's for the given point there, and all right. So now we want to look at a secondary point, which we'll do in purple. If you read the checkpoint, it wants to rotate all the way around, right? So we know, so first of all, let me ask you a question. Given this velocity, will my particle here move clockwise or counterclockwise in the circle? Well, that's for you guys to answer. What do you think? Oh, got one counterclockwise. Okay, let's take a look. So if we go down, right, we'll be moving against the clock following the velocity vector. So if you follow my point, we're interested when the particle is at y equals +2. So we've got to be careful there, because this here is x equals +2. This is not the point. We're interested in y equals 2 right here. Okay, yeah, at 90 degrees. So I'm gonna make my green point here. Now, if I move around in a circle, I've got my velocity vector like so, and then let me get back to, and I've got my, that wasn't great, but I'll just call it my acceleration vector like so. Okay, now you'll notice here a is still going to be equal to 8, because it's just v squared over 2. V hasn't changed. R, or v squared over r. R hasn't changed, and v hasn't changed. But now it's going to be negative in the j hat direction at the point we're looking at. Okay? It's pointing down. So we use a standard right-hand coordinate system. When we go to the, you'll notice the velocity now, though, is also pointing in the negative x direction. So v will be equal to -4, but now in the, this is going to be meters per second squared, and this is going to be 4 meters per second, but this will now be in the I hat direction. Okay? So that's what's going on there. And it's important to note that you can express this pretty easily as a rectangular vector point by point. It gets a little harder when you do it dynamically. When you do it dynamically, you're really going to want to go to r hat, theta hat for polar coordinates. But again, this is hard. This is hard to do mathematically rigorously. And in fact, the expressions can blow up quite quickly. What I mean by blow up is imagine having equations that are like 5 or 6 pages long. So yeah, you won't do this. And when we do this, we'll do it in an ad hoc manner. That's kind of frustrating. We won't be doing r hats and theta hats in a rigorous manner. So does this clarify this a little bit more than yesterday about what you're looking for here and how to express everything in terms of vectors? Yeah. Okay. I'll take silence as how do we get v? V is given. So that's the important thing to realize is v is interpreted. V is right here we have v is minus 4 meters per second. So we can just take the magnitude of this vector. Right. So if we start over on this side, let's go back to blue. So v is, so it's given that v equals minus 4 j hat meters per second. Right? The magnitude of v, or the speed, is equal to 4 meters per second. And this is the v that goes in the acceleration. Okay? No, the velocity is, Fatima, the velocity is not constant. The speed is constant. You can't call them the same thing. That's the error there. The velocity is actually changing because the direction is constantly changing. The speed is constant, but the velocity very much is changing. And this is where we say that they're different things. So you can't just, yeah, okay, good. I need to, thought I had a cough drop here, but that was incorrect. All right. So, does this make sense then? We all right here? Okay. All right. So now I sort of want to wrap up our discussion in Chapter 4 with these frames, with this idea of relative motion. We started yesterday by talking about a water balloon cannon, right? Where you can fire a water balloon cannon. You know, you have some sort of, I can't really draw a cannon, but say you can fire water balloons out here at 30 miles per hour. And then say you're on a car. You'll all see my great art skills. Yeah, this is why I was not a fine artist. Wheels, person with the water balloon cannon here. And if the car is moving at an additional 20 miles per hour, then it depends who sees what velocity, right? You would still see the water balloon cannon being fired at 30 miles per hour. I would see it coming at 80 miles or at 50 miles per hour. Another thing of looking at the main reason for looking at frames, though, is to interpret different motions. And we talked about motion, you know, if we go forward one slide, we have more room on the next slide. Right? If we have, I don't have more room on the next slide. I have more room on this slide. If we see, if you're sitting next to me on a train, and I throw something up and down, and we're sitting in the same frame, you'll see it just move up and down, like the pen I'm making here. But if you're outside the train, you'll see this path. And as we concluded yesterday, both of these are correct. And what frames allow us to do is translate from one interpretation to another. If this is, we can call this frame A and frame A prime. Basically, what we have to know about physics is that physics, the laws of physics apply in what we call an inertial frame. And that means that the A of the frame equal to 0. So Newton's laws and the physics we described does not hold in accelerating frames. Now, what's interesting about accelerating frames is that if you look at an acceleration, you can look at things accelerating from a non-inertial frame. So what we're talking about here is where you're making the measurement. So a good example of this is a merry-go-round. And that's actually, if I can get this to work, which was okay yesterday, I need to close some of these tabs. I need to close some of these applications, actually. Oh, wait a minute. Maybe I can do that one. Hold on. You know, it might be too much to find this movie I want to look for. But anyway, it's the difference between if you know what a merry-go-round is or a carousel. A carousel is a non-inertial frame. It's rotating. Now you can set up math for rotating frames. That's not hard, but the laws of physics don't apply like they normally do. And what that means is that, so for instance, if you're in a merry-go-round and you throw a ball, it will all of a sudden look like it's starting to curve, like it'll do something like this, and it'll look like it's curving by magic, or that some force is working on it. Now, the reason why we don't call those real is because we can analyze these frames, or these motions and dynamics, from a non-inertial frame, or from an inertial frame, rather, sorry. And in the inertial frame, again, that's where the acceleration of the frame is equal to 0, we can eliminate these fictitious forces. So centrifugal force, if you're in a car, is a fictitious force. If you turn the car, it feels like there's a force pushing on you. If you analyze that from a non-inertial frame, there's no force pushing on you, and the motion is explained quite easily. As the car itself actually pushing at you, keeping you in the car. So like I said, with this, we're not gonna get questions on this part at the moment, but it's important to be exposed to it and understand it a little bit. So as you can see, they have it's about looking. If you've heard the frame relative to, so you can look at velocity as of B in A. Okay. And the next slide is the most interesting one, because you'll notice that we can only, when we set up our frames, so positions in different frames are related here. So the XP from A is equal to XP from B plus XB from A. So you'll notice when you take this, and you take the derivatives to get to the accelerations of the frames, in order for it to be inertial, this term has to go to 0. Okay, that's really the big thing here, is that when this is 0, the accelerations are the same. And then when the accelerations are the same, the laws we've talked about and the laws we're going to talk about apply. Okay, so I don't want to spend an enormous amount of time on this because it's sort of secondary to what we do, but you can see that it applies in 2 dimensions as well. All right. So let's move on to the main topic of today, which is forces. Everybody loves forces. All right. That one. Okay. Force in motion. Fun times for all. So we're getting to the main meat of the course, which is Newton's laws. And Newton's laws will provide a framework for us to look at the course, to look at physics. Now, what's interesting about that is that Newton's laws really provide this framework in which we can look at trajectories and motions. However, they're also going to open the door up to a much larger framework, which we'll also look at in this course as well, which is energy conservation. And we're going to connect energy to Newton's laws. Newton's laws will be the central point of this particular course. But if you study advanced physics, you're going to see that the energy paradigm is how we solve complex problems in physics. So, because we're in a new space learning new things, though, we have a lot of fun definitions to look at. So, force is a push or pull, right? I'll get my schedule, and if I pull or push or move it, I'm exerting some sort of force on it. All right? So forces cause objects to accelerate, as you can see here. All right? Now we'll focus on Newton's laws. Newton's mechanics is valid for everyday situations. So what does this mean? So when you look at physics today, you'll notice it says here it's not valid for speeds which are an appreciable fraction of the speed of light. It's not valid for scales on the atomic structure. And it's viewed as an approximation of general relativity. That all sounds nice, but what in the world does that mean? So a lot of times people will say fairly incorrectly that Newton's laws are wrong. Well, the way I like to look at it is this. This is the universe. This is everything that can be explained between these two bars, right? If we understood everything here, we would understand the universe in its entirety. So I am not, unfortunately, a blackboard troubleshooter, so I don't know what to tell you. Can you hear me at least? Yeah. Okay. Yeah. Follow your fellow students' suggestions. So, because when these problems come up, I have no idea what to do about them. So unfortunately, I'm sorry about that. Okay, so when we get here, we have Newton's laws. We're thought to explain everything, but Newton's laws explain about this much of the universe. All right, and what we found with Newton's laws is we got more. At first, physicists thought that Newton's laws explain the entire universe, but they don't. And eventually, I'm going to leave E and M out of this because it gets harder. But yeah, no, we're getting there. But eventually what we find is that general relativity, no, not text, explains like stuff from here to here, and quantum physics explains stuff from here all the way out to here. Now, the only place where quantum physics and general relativity lap is when you put them in these regimes where they look like Newton's laws. All right? But their fundamental structure makes them incompatible. That's why I didn't have them overlap. And basically, it's easy enough to look at the difference in that fundamental structure. General relativity assumes that the universe is continuous, right? There's an infinite number of points between these between these 2 points, right? You can always break this down further. Quantum mechanics looks like this. It's discrete, right? It's not continuous. However, you might be saying, well, wait a minute, but they seem to work over here. Well, yeah, if you put enough points in here, right? You can see for this little part here, I'm not going to do the whole line, but if you put in enough points, it starts to look like a straight line, but we know fundamentally it's not made out of a straight line. We know it's not continuous. So here, where there's lots of particles, yeah, they overlap. They look the same. And the weird, spooky action at a distance, or the weird stuff, that all goes away. And you don't see it anymore. I'll move this. Try to get my mic in front of me. You don't then need to see all the stuff I have. So that's the fundamental difference between quantum physics and general relativity, but why they overlap in Newton's laws. So Newton's laws are not wrong. They're just a easier simplification of two more complex theories that explain everyday phenomena. Okay, and they were definitely developed first because they do describe everyday phenomena. So I hope that brings some clarity into sort of what's going on with physics. Because if you watch TV, they really do a bad job with this most of the time. A very bad job indeed. Okay. So before Newton's mechanics, some influence was thought necessary to keep a body moving. The natural state of an object was at rest. This seems intuitively reasonable due to friction. So let's look at Newton's first law and understand this. Newton's first law says that if no force acts on a body, the body's velocity cannot change. That is, the body cannot accelerate. That's what we see here in this starred part here. Well, really, the way Newton's first law is often presented is that objects in motion tend to stay in motion, and objects at rest tend to stay at rest unless acted upon by an outside force. Now, what does that mean? And why does this before Newtonian mechanics make intuitive sense? Well, just pick up something in your house and start rolling it or push it somewhere. Not a person or a small sibling or something, but just pick up something. Here, oh! I don't know, cough drop. So, I don't know, let's take this charger. Alright, if I move it on my hand, if I set it, can you see it? If I set it in motion, it doesn't, I can't have to keep pushing it for it to stay in motion. So, so even though Newton's, we've grown up hearing Newton's first law, if you really think about what it says, it's not intuitive because nothing you've ever seen has behaved that way. Okay? Nothing has ever just kept moving when you keep moving it. And so what this shows us is that anything that affects motion must be caused by a force. And that causes us to catalog it or find what's causing it. And of course, if you look at friction as a force, you know, and it's reasonable to do that because if you go on something like, say, an ice skating rink, the same applied force, the same push, can cause an object to move much farther than, say, on a wooden desk or on a table. Okay? So Newton's first law sets up what forces do. And Newton's second law sums up what forces are. All right? So Newton's second law, we're just going to write it because we'll write it a lot, is the big central equation, of course, which is F equals mass times acceleration. And force is a vector. Okay? So force has its own unit, the Newton. All right? And 1 Newton is obviously equal to a kilogram times meters per second squared. As we pointed out, forces are vectors. All right? And the net vector, or the net force, is the vector sum of all forces on an object. So we can write F net is going to be equal to the sum of the individual forces. All right? Now, one way to think about that is think about me right now. Right? The net force on me is 0. How can we tell this? How can I conclude that reasonably? I'm waiting for you. You are not. Yes, I am not moving. That is correct. I am. So the sum of the forces equals 0. Right. Does that mean there are no forces acting on me right now? Well, we're about to. Exactly. Good. So what about my weight? Well, I have a weight. Weight is pulling me down, but the force of the chair there's what we call a normal force pushing me back up. So there are forces acting on me. They all add up to 0. So when we look at this, expression here, this will have my weight and my normal force and all the other forces acting on me. ... That may or may not be there. And we'll define the normal force in a minute, a little bit better, not much, but a little bit. So all my forces, individual forces that act on me, are in here in the sum, but they better add up to 0 because I ain't moving, right? So, so the principle of superposition is an important one. All right, it means that all the forces can just add together and act as one force. All right, so the resulting force on me is no force at all, but that doesn't mean they're not there. So another way of saying Newton's first law, with a little bit of math here, is that if no net force acts on a body, that is, if the sum of the forces is equal to 0, the body's velocity cannot change. That is, the body cannot accelerate. That doesn't mean the body's not moving. All right? Remember, if v is constant, so let's say v equals 8 meters per second, and it's not changing, right? If you take the derivative of that 8 meters per second, it's still going to be 0. So don't get caught in that trap of thinking that only things at rest can't accelerate. You're always going to want to look for you're always going to want to look for that constant velocity in the problem, all right? To see if your velocity is constant or not. Okay. Right. Okay. So we just talked about this with frames. An inertial frame is one in which Newton's laws hold. It's also one that is not accelerating. Okay? So you'll notice, so some examples: a frictionless puck pushed from the North Pole viewed from space, the same situation viewed from the ground. However, over long distances, it's important to point out, over long distances, the ground is a non-inertial frame. This brings us to ideas of global versus local. The ground is a local inertial frame. It is a non-inertial frame globally, which means on long enough scales, it no longer meets our criteria. You're going to see this often in physics, going from physics 1 to physics 2 and advanced physics. When you have something like the Earth or something that can appear weird, right, and you need to do analysis on it, you just take a small part that looks like a constant line. And then you use the physics of constant lines, and you can use calculus or a function that describes the wiggle to add them all up. Okay? That's something you'll be doing quite a bit in this class. That's sort of essentially the, if physics were a verb, that would be doing physics, basically, is doing that. Oh, yeah, what's going on? Wait, froze? I'm still talking. Yeah, sure. Can you hear me? Everything's fine? Okay. So basically, if physics were a verb, doing physics is sort of breaking up complicated things into smaller things, okay, into these tiny segments that we can apply simple models to. So usually our models get hard, and we apply, it's easier, we find, to apply lots of little simple models instead of one big complicated model. And you'll find we do this frequently. And where it comes to here to our description of frames is that the Earth, the ground we stand on right now, is locally an inertial frame, right? But if we start to zoom out and look at the whole planet, it's a non-inertial frame, right? So it's globally non-inertial, but it's locally inertial. And that's important because basically that means that we can look a little slice and say something's inertial, even though it's not inertial. And this also begins to explain why Newton's laws are an approximation of things like general relativity. You can look at the Earth and globally as a global system and define inertial frames in general relativity. whatchamacallit, and then start looking at things in a much broader picture, but that requires a lot more sophistication than we have. Essentially, the easiest way to see if you're in a essentially, if you want to ask yourself, am I in a inertial frame? Get an object and let go of it, and if it doesn't move, i.e., doesn't fall or anything, you're in an inertial frame. So if you put something on your desk and you let it go, you'll see it doesn't move. You can say that this is an inertial frame. Interestingly, and this gets to general relativity, if you're skydiving, right? If I'm skydiving and I'm falling with my channel changer and I let it go, then that also satisfies the definition of an inertial frame because it's not going to fall any faster than I'm falling. But that makes things tricky. That's way beyond the scope of the course. But that's when things start to get really fun. Is thinking that way, and then using those definitions of inertial frames, you start to be able to construct general relativity. You need a lot more, but that's the way to start thinking about it. But we're going to consider non-accelerating inertial frames. That's where Newton's laws apply. So we want to do this easy little checkpoint here first. So this is really a chapter 3 checkpoint, just redone. So if we assume the ground is an inertial, or generally we assume the ground is an inertial frame, right? We already said that. Which of the 6 arrangements correctly show vector addition of forces, F1 and F2, to yield a third vector, which is meant to represent their net force? We did this checkpoint in chapter 3, but now we're adding forces. It's not abstract anymore. So which one of these correctly does vector addition? I'll give you a hint. There's 3 of them. So okay, so we've got E and A. So in order to add vectors correctly, you have to have F1 connect to F2 and make a triangle. That's not really happening here. Or you can make a parallelogram from F1 and F2. So if you have F1 and F2 like this, you have to have the correct addition will be something like this. So this vector this is bad. Okay? Now let's look at E. E is the same setup, but the vector very much here goes in the way we expect with the parallelogram method. So E is correct. All right? Now, it seems like you've got the rest of them. You'll notice with C, let's look at C. C starts with F2. That's F2 plus F1. We start at one vector, end at the other. So C is going to be correct. And D, we start at F1. We go to F2. We add, so D is correct. So you'll notice that the difference here, just to point them out, is this one is F2 plus F1, and this one over here is F1 plus F2, and we know that addition is commutative in vectors. Keep in mind multiplication may be, but not necessarily. It depends whether you're doing a vector product or a scalar product. Okay. So C, D, and E are correct. We can see the book loves us too. All right. But you'll notice when I wrote Newton's second law, oh, that's blue up there, F equals ma, we introduced a new quantity without really talking about it, because we all have an intuitive notion of what mass is. No one's being introduced to it. But one of the things we're going to need to understand is that mass is not equal to weight. All right, and we're going to see that as we go along today. So, mass is often described as how much stuff is there, but actually it's a measure of inertia. It's a measurement of the body's resistance to change in motion. Basically, the mass is informative, and what the mass tells you is how hard it is to push or pull something. Okay? I'll move farther back from the microphone. It tells you how hard it is to push or pull something. That's all. That's what it really does. So think about a baseball or a toy ball of some sort and a refrigerator, right? We assign more mass to the refrigerator because it's harder to push and pull than the toy ball, right? So mass, but by giving mass, making it quantitative, we know exactly how many balls it would take, or toy balls, to make it just as hard to move as the fridge, and that lets us compare and start to solve problems and quantify things. So that's the motivation for quantifying mass. All right, you'll notice it is not the same as weight, density, or size. All right. So if we apply an 8 Newton force to various bodies, right, we'll notice that the force is the same in all of these examples here for each of these points. Take a look. So you'll notice that the force is 8 newtons, so it would feel the same, but if the larger the mass, right? So to get the mass, you have 1 times 8. That would be 8 newtons. If you have the mass is equal to 2 kilograms, the acceleration then must be 4 meters per second. So the lower the mass, the higher the speed, or the higher the acceleration. Sorry, now I'm doing it. And vice versa. All right. So again, this uses this Newton's second law here. Okay, so the same force can be applied to the same mass and accelerate that mass differently. And basically, if you apply the force to each of these masses, it'll lead to these different accelerations. Okay, and then once you have these accelerations, you can use your Chapter 2 stuff to figure out the trajectory. All right. Okay, so Newton's second law is as we've written it before, right? So what you do here is you'll find that on one side you have all the forces you're adding up, right? Your F net. So when you identify forces on a problem or that are acting on a body, you'll add all of those up on one side of the equation, and you can always set it equal to MA on the other. This is pretty cool because it always gives you an equation, right? And that's sort of the part of the class we're entering now, is this building of equation. We're going to build simple models to look at simple systems. And F equals MA is really that model. And that's pretty cool. And that's all you do is first you identify the forces acting on the body. Then you sort of draw them to figure out where their directions are so you can quantify them correctly. Then you add them together. And then you set them all equal to MA. And that will give you an equation. Now, because it's a vector equation, you'll find that you conveniently get 3 equations. You get an x component, y component, and z component. All right. And this is an important thing to note. The acceleration component along a given axis is caused only by the sum of the force components along the same axis, and not by force components along any other axis. All right. So force in z can only give you acceleration in z. A force in the z direction cannot give you an acceleration in the y direction. We're going to see that when as our motions get more complicated, new ideas will be added that will work differently, but those won't be forces. That's why they're called things like torques and other things like that. But we'll get there way later. So this is Newton's second law. Is there any questions on this so far? I want to be sure I answer anything in case I don't get too lost in my own head before people have questions. I meant to say So chapter 4 represents the end of the chapters that will be covered in exam 1. I'm trying a new thing where instead of making the first exam cover 6 or 7 chapters, I'm having the final cover a lot of chapters to give it more of a final-esque feeling. I'm trying to make the first test a little more manageable. So it worked really well last semester. The students seem to really like it. So I'm going to stick with it, see how it keeps working. It may or may not. So we're officially into test 2 stuff. But the first exam, I don't know yet. I know the date, so basically I need spring break to figure it out. I'm going to give you your first exam after we come back from spring break, which is subject to change. I say that because they change things almost daily with how this is going. So it's my understanding as of today that we will have our normal spring break because we're on a different schedule than those other CUNY schools where the whole message was about. So the idea is that we have it when we get back on that first Thursday, probably. The calibration period, again, you have to look that you really have to. It's going to be hard for you guys. So so Kingsborough, LaGuardia have a different semester system, so you can't follow the CUNY calendar one for one. For instance, they end in May, so their semester is almost done. Our semester just started. We're on a 12/6, and I've been getting emails about this. So you have to follow the. Yes, it does not apply. If you look and read the email very, very carefully, you will see that it applies to 16 colleges, and we're not one of them. So, yeah, but that doesn't mean that scheduling at LaGuardia won't change. Honestly, yeah, no, I know. It's this often whenever. The 3 campuses that are on a different schedule, we've tried. CUNY likes us on this schedule because it's better for you guys. But when a crisis happens, there's no one central place to look for our campus. You have to follow the LaGuardia site because we're on a different schedule than the rest of CUNY. That's just true. So, yeah. So LaGuardia is in its own sort of, along with Kingsborough and Gutman, I think it is. We're on our own schedule, so we do things a little differently. So yeah. But I like I said before, the option to not follow your LaGuardia email is no longer there. I can't forward things to your preferred email because I'm not sending you everything. So you really need to check your LaGuardia live email. It's just not an option anymore. So I know some of you don't like to do it, or it's a pain in the butt, but you can't not do it anymore because you're going to get messages from the provost, from the registrar, from other people about when you can drop classes, when you can add classes, what modifications they're making. This is information I don't have. And your other professors probably don't either. So check that live account, get it set up. That's where the school will be sending things to you. So keep that in mind. Yes, and CUNY Central explicitly accepted LaGuardia from them. But CUNY Central will probably use your live email, so unless you have it forwarded, but you'll have to set that up. Okay, so let's move forward then. So some things to point out that it doesn't hurt to hear again and again and again. So if the net force on a body is 0, the acceleration is 0. That does not mean the velocity is 0. Remember, constant velocity, you take that derivative, the acceleration is still 0. So if this is true, though, if the acceleration is 0, the forces and the body are at equilibrium. Again, the sum of the forces may be 0, but there may still be forces. Okay? So You'll notice here that we look at, we have our units of force. So you'll notice that the pound, remember we talked about, hold on, what is it I wrote here? Weight, oh no, I messed that up. So I'm just going to do it in terms of, so weight versus mass, right? They're not equal. And you'll notice they're in different columns. Look at what's interesting here. So the force Newton is comparable to pounds, which is a force. Pounds are not a mass measurement. All right, you'll notice under here mass we have kilograms. Kilograms and pounds are in different columns. And in this sense, it actually doesn't make sense to convert from one to the other. Now on Earth, you can come up with an equivalence, but they're fundamentally different types of units. You'll notice the mass in the British system is a slug, okay? And 1 pound is 1 slug per system. Now the CGS system is an old system where we use kilogram or centimeters and grams, and a force is known as a dyne. All right. Now it's actually mass doesn't change no matter where you are. Exactly. It's just as hard to move you in. When we look at a modern understanding of mass, mass is the collection of stuff that you are. You know, it's essentially, you know, like your inertia is your stuff, how many atoms you have, and that doesn't change, right? It's a counting problem. However, your mass can change because your mass, or not your mass, I'm sorry. It's been my head is, it's not been a fun week. Your mass won't change, but your weight is equal to your mass times the acceleration of gravity from where you are. So this has one value on the Earth. It's equal to g. It's equal to something else. We could call it g Mars. On Mars, there'll be a g for the sun. We'll actually learn how to calculate these different g's. But this is the one we use on Earth, right? This is our 9.81 meters per second. We can call it Earth if you want. Earth. I think I spelled that right. I'm not a very good speller. I'm okay with it. But yeah, 100 kilogram person on Earth is still a 100 kilogram person on Mars. Now, what's interesting is that you can't say that where people actually get it wrong. It's the kilogram users who are generally incorrect when they say I weigh 10 kilograms. They don't weigh 10 kilograms. Weight is a force, not a mass. So, in some sense, it's indeed the rest of the world. If you say, well, my mass is I'm this many kilograms, that's probably more correct. That's what I think I hear most people say when they talk about their mass. But usually we go between weight and mass in a very strange way. And I say strange because they're not the same unit. Okay? So, now we're going to learn about one of the tools that can make very difficult problems into very manageable problems. But don't take it for granted what we're going to go over, because what we're going to go over sounds very simple and trivial. However, when you solve problems, they won't be simple and trivial. So we're going to see this idea of the free body diagram, and we're going to draw it to get an idea of how to use it and apply it. Okay? So we have here a puck with different forces acting on it in 3 different situations. All right? So in the first situation here, right, we have this drawing, and there's this force that acts on the puck here. Right? So there's the force. You'll notice we make a dot here, and we draw the force acting on the body. So we approximate our puck with a point, and then we put the force acting on the point out. This is a free body diagram. And this is as simple as it gets. One force, one free body diagram. Now, when you look here at part B, we still have F1, but now we have another F2 here. All right? And what this allows us to do very simply is if we look at the x direction, we can see here that the sum of the forces in the x direction will equal F1 minus F2. And Newton's second law lets us set that equal to ma. Okay? So, so we can do that, and then this free body diagram translates to our model. And here it translates very easily, right? And that's it. It seems simple. But it can get a little trickier, especially if you have 3 or 4 forces on here, which is a situation you may see. Now, let's look at C here. All right, situation C. So now you'll notice we have F2 and F3. And now F2 is still pretty simple, but F3 has got a little bit of X and a little bit of Y. And so what we do here is we would sum the forces in the X direction here. That's going to be equal to F3 cosine theta minus F2. That's going to equal MAX. Hold on, I'm having trouble with this pad here. I'm not going to move all that individually. And the sum of the forces in the y direction will equal F3 sine theta all right, and that's just by itself, and that will equal MAY. So I know it's hard to see the one in the x direction, so I'll point out what everything is again so you can write it clearly yourself. That's the sum of the forces in the x direction equals F2 cosine theta. That's just the x component of this force of F3, right? And then that's going to be minus F2, and that's going to equal MAX. And then we're going to have here Fy equals F3 sine theta minus just this component equals MAY. All right, and that's it. That's how we analyze this free body diagram. Okay, so that's how we set up the equations. So what basically the point of a free body diagram, which is this point, and remember free body diagrams only have forces. So the only body shown is the one we are solving for. The forces are drawn as vector arrows with their tails on the body. A coordinate system is shown. You'll notice you need your coordinates because you'll need to get your angles down. Acceleration is never part of a free body diagram. Only forces on a body are present. Okay? So we sum these and we can find the accelerations, but you'll notice on the diagrams themselves, we don't have an acceleration. Okay? And we use these free body diagrams to set up our models for our problems. All right, and that's what we're going to be doing for probably the next week and a half, 2 weeks. Okay, or at least through the break. So, are we good there? All right. Let us. Okay, it is 2:02, so let's take a that's a good spot to start on a good 10 to 15-minute break. So let's come back around 2:15, and we'll go for the rest of the hour, okay? And I'll keep recording so that you can, if you have questions and your technical questions or answering each other's questions, you can refer back to that. But I have to get some water, so I will. All right. Hold on. Hello. We still have a few more minutes of break left. Hold on. Okay, that's better. No, I haven't graded the lab reports yet. I was going to get through the. I was going to try and do them all this weekend. Because I'm still waiting on the first lab report from Physics 2. I realize they don't have much to do with each other, but that's when I'm, in recalibrating myself. This is when I'll get to them. So I had to make a bunch of stuff for the other classes. So yeah, I'll probably get to those this weekend. All right. So let's get back to it. Are there any questions about the stuff we've talked about with free body diagrams? We're going to see a ton more of it, so don't worry too much. You have a problem in the last two classes to log in. So there will be the video. I figure that might be an issue, so that's exactly why I'm recording everything. So when you're in the menu, before you, not in the chat room, right now you're in the room, but when you're in the Blackboard Collaborate menu, on the upper left-hand side, there's three bars for the menu, and you can click on the recording. So that's precisely why I have that in there. The lab is online. You will never miss lab. Labs are always online. I want to be very clear. I guess I'll have to say it however many times I have to say it. Labs are online. You will have a video instruction which you'll watch for so that will be coming next week. But the lab is online. There's data, and you just do the data and pretend like you're doing the lab, and that's all you do. That's in the instructions. Lab is supposed to be hands-on, so you sitting here watching me talk about lab like this, in my mind, is just not useful. So you need to be doing stuff. So do the lab. My Skype is usually on all the time. So right, there's no online lecture. You will have videos you need to look at for the lab, but we're not going to meet like this for the lab. That's not happening. If you have questions, though, I'm having what I'm calling extended office hours, so I'm making myself available after each class. I'm just, if I'm around my house, you can give me a try. I mean, I'm here, so if it's not too late at night, I'll probably pick up, and so you can give a Skype call or a Skype chat. That's how I'm managing my office hours. The videos are on Blackboard. You have to access them through the Blackboard Collaborate Ultra, though. They're not in the content section. So that's what I was trying to explain before. You have to go to the Blackboard Collaborate, where you select the session. On the upper left-hand side, there will be 3 parallel bars that look like this for the menu. You should see them now, but that's not the right one now up there. But there's these 3 bars that look like that for a menu. It's a pretty common icon. And you click there, and you should be able to get access to the recordings. They take a while to process, though. So if you wanted to look at today's lecture, you probably have to wait till this afternoon or till this evening. Okay. So they should be up there all semester long, and you should be able to look at them whenever you want. So, like I said before, I don't really know how to do the Blackboard support. If you're not logging in or having issues, I would contact Blackboard's support immediately and see how they can help you. Because I can do many things. Tech support's unfortunately not one of them. So, anyhow, going forward, let's continue with our discussion of forces. That's not good. Hold on. That's my phone. And I have an iPad that's far away, so we'll just have to let it ring out. Okay. So, going forward. we've got a checkpoint. It's always a good way to come off a break. We have a figure here that shows two horizontal forces acting on a block. So if a third horizontal force also acts on the block, so that means you've got to add a force to this diagram. What are the magnitude and direction of F3 when the block is stationary and B moving to the left? So basically, take a look at what's happening now, and let's see what force do you have to add for the acceleration to be constant, or the acceleration to be 0 rather. Okay, so I'll let you work that out for a minute or two, see if you can figure out that problem, and then we'll go over it. Just make sure that that person doesn't call me back again. Okay, so basically, you're going to add an arrow, right? So let's look at a few things. If you add an arrow up, a force up, does it change the horizontal acceleration? No. Good. So let's clear that one. We don't want that. So in order to affect the horizontal acceleration, we only want to look at the horizontal acceleration. Now, they want the block, if the block is stationary, would we add the force going to the left or the right? Well, if we add it here on the right, that's just going to cause a net force to the right. So that's not going to work. So we want to add, right now, the way to look at it is right now we have 5 minus 3 plus x equals 0. Right? That's basically our equation. In fact, I'm going to take it away from algebra. Write it like we should. F3 equals 0, right? So if we solve, we want the net forces to be 0. So we solve for F3 equals minus 2, right? So that would be 2 this way. Now what about part B? So in part A, that's fine. But if the block is moving 5 meters per second at a constant speed of 5 meters per second, for part B, what's A? Take a look at it again. Concentrate on this word. What does that tell us about the acceleration? It's 0. Good. Right? So then we still have this case applies from part A. So we'll see here that F3 is also equal to -2. We want to use our units correctly. Yes, Tala. Yes. F1 plus F2 plus F3. Sorry. F1 plus F2 plus F3. Yeah. You're right. Because it's -3 in this direction. This is F1, and this is F2. Well, I don't know if it's easier, but so if you want, you can call this F1 and this F2, and then we're just saying F1 plus F2 plus F3 cases will equal 0, right? Now here, you're just putting in the minus signs because that's what they are. Right. So the way to write this, so this is generally correct, right? Now you would write F1 minus F2 minus F3 equals 0, really, as if you want to look at it there. All right, this is an important point, so is everyone clear on what's going on here? You have to be able to interpret here. This isn't straight math. Yes, how Mina wrote it is correct. But they're all correct. It's all about interpreting and not interpreting. This one makes no assumptions on the sign. This one is specific for the problem we have in particular. This is just a way of writing it once we've assigned it, and they all give you the same thing. Okay? But it's important to realize that you have to the goal here is to interpret the problem and apply it to the general equation. Yes, constant speed means acceleration is 0. Okay? All right. Okay. So as we go forward, it's 2 to both sides. All right. So we're going to look at some particular forces. Now that we sort of talk about what force is, we want to see what we can apply. So as you can see here, gravity that works on the Earth, well, gravity works everywhere in the universe, but the gravity due to Earth will be encapsulated as the force of gravity, that's your weight, will be equal to the mass times the gravity which you feel, for that acceleration. Now, in free fall, right, you have your Fg is pointing downwards and is equal to m times minus g. Remember to be careful with those minus signs, all right? So Fg is equal to minus Fg in the j hat direction is equal to minus mg j hat. You'll notice here in the vector they don't put the minus sign, and then they put the minus sign in here in particular. That's exactly what I was talking about in the last checkpoint. You have to be able to interpret. There's no one simple way. You will be expected to interpret. No one is going to automatically put all the signs correctly because that honestly changes from problem to problem to problem. So your goal is to look at the signs and do that correctly. And you can only do that with practice, unfortunately. It can be tough to do, but you want to keep practicing it, working on those homework problems, and that's the kind of stuff you want to get out of it. Okay. So this force still acts on a body at rest. We did that when we talked about me sitting down. So again, that's one of the many forces that will always be acting on an object. And we just have to learn about more forces that will cancel it out to explain me not moving. Okay? All right. So we're still on weight here. I thought we were going to go to another force. So to one body, so let's see. So weight is Fg, all right? And you will see me write it this way interchangeably as Fg or W. The weight of a body is equal to the magnitude of the gravitational force on the body. So I guess they called it gravitational force here. Yeah. So the gravitational force Fg, I started calling it weight on this slide. Sorry about that. So right, weight is just equal to Fg, and it's due to that gravitational force. So that's not a helpful example. So measuring weight. So when we measure weights, if we went in the lab, you could use a balance to compare a body of known masses. So usually what they do is you have known calibrated masses, and you put them on one side of the scale, and you put your unknown on the other side of the scale, your knowns and unknowns. You sort of set it up like a mechanical algebra equation. Again, weight is not the same as mass. A pan balance will read the same for different values of g. Scale will read differently for different values of g, right? So weight must be measured when the body is not accelerating vertically. So in your bathroom or in a train, but not in an elevator. So now weight, why do we, an important thing before we move on to the next force, because weight just seems to go on and on and on forever, is weight is looked at differently than the gravitational force, because your sensation of weight is not actually the gravitational force. It will be due to this force here called the normal force. All right? And if you don't believe me, jump off something safe at a safe distance. Most of you are still young enough where you won't hurt your knees by jumping off something. I can't do it anymore. But if you've ever gone skydiving or something like that, gravity is still pulling you down, but you feel weightless. And you feel weightless because there's nothing pushing you back up. Your sensation of weight is gone. An easy way to feel this is to go to a bathtub or go into the ocean or swimming pool, and you will feel lighter. It'll be hard to move because you have to move through water, but your sensation of weight will lessen because you're floating on water. Hopefully, you're not sinking. That would be bad. So your sensation of weight is really a reaction force defined by what we call this normal force, all right? And so if you're standing on a surface or sitting on one, the pushback on you from the surface is called the normal force. And I want you to notice that this force is called normal not because it's not strange, but it's called normal because it's always going to be, it's going to make a right angle with the surface, okay? So it's normal in the mathematical sense. So if you have a slanted surface, right, your normal force is, oh boy, it's going to be hard to draw. Your normal force is going to be, you're going to notice it's going to make a right angle to the surface, okay? So your normal force is not always opposite of Fg, okay? And again, your weight will often put here is equal to F. Well, I'll show you how we do weight in a minute. So when you look at this, oh, hold on, I'm gonna drink water. So when you look at this, the normal force, yes, Tala. No, that's just what I'm talking about. It is only happens to be equal to G here in this setup. You'll notice if you're on a ramp like this, F of G still just points directly down. So you'll notice here in the drawing on the side, this is the normal force, this is G. They are not equal and opposite. They happen to be equal and opposite here. The normal force is always normal to the surface, okay? And so if we make a free body diagram of this picture, you'll notice we get the normal force going up and gravity going down, all right? And your sensation of weight, the measurement of your weight comes from gravity, but the sensation of weight comes from the normal force. If you take away the normal force, you're just falling down and you feel weightless. Okay? You're welcome. So I think that's what we have here. I think we're going to do apparent weight next. Right. So the normal force, your sensation of weight. Let's look at it before we do the checkpoint. I want to go back and derive the next slide from here because I think it'll be more useful. So let's look at the free body diagram here. And I'm going to do the equations on the other side. So here we can see that, but I'm going to do them in general. So Fn minus mg, right? That's going to equal, because that's the f of g, it's going to equal MAY. Okay? Now, we can solve for f of n. That equals mg plus ay, and f of n is going to equal m times g plus ay. So you can see here that if ay is equal to 0, all right, just in this case, then this a will go away, and then you actually will have that fn is equal to mg. But if you're accelerating, like say you're in an elevator, as you accelerate up or increase, your normal force will increase, and your sensation of weight, your weight will actually increase. What happened to May? I don't know what May is. I hope it comes after April. What happened to MAY? Oh, I see. Oh, right. What happened to M? Okay. You can see the, I think we've just found the limitations of keyboard typing. Yeah. So no, Tyler's right. I forgot to put an M on the second equation, and then that's what lets me take the common factor out in the N. So I just forgot to write it out. So, yeah, no, it will. I'm sure of it. Yeah, now it makes sense. So I think the limitations of the keyboard and my ability to recognize patterns. Yeah, and it's just getting started. It's just getting started. Both in the bad and calendar-wise. Anyhow. So, the sensation of your weight, which will sometimes be called your apparent weight, can actually change if you're, say, on an elevator. If you're accelerating up, you'll feel heavier, and you will be heavier. And if you're accelerating down, vice versa, you'll lose some weight. You won't lose any mass, though, so don't get too excited. All right, so if we look at that, if you're wondering about those equations, they're written here. All right, I just wanted you to see how to construct this equation from a free body diagram, because that is what you will be doing when you solve homework problems. All right, so hold on. Sitting down a lot is not good for me. All right, that's why I have to walk during the breaks. It's very opposite of what we do in the classroom. Okay, so in figure 5.7, is the magnitude of the normal force greater than, less than, or equal to the block if the table, okay, so we want to look at this figure, 5.7. So we want to imagine this figure is in an elevator. And we want to know, is the normal force greater than, less than, or equal to mg if the block and table are in an elevator moving upward at constant speed or increasing speed? So we just kind of did this, right? So I'll do part A. So if we look at this equation, right, we have Fn here, and if we're moving at constant speed, A will be equal to 0, and Fn will be equal to mg. So A will be equal to, and now I want you to try and do B. What do you get? I'm going to erase the work here so it's not confusing. Hold on. This is all just, this gets out of control. So I'm deleting these so they don't confuse you. So we're done with A. You're done with A, you can delete the work for A. So the thing to look at here is B greater. What do you think for B, everybody? Do we agree with Daniel, or is it all some sort of... Wow, so we have some disagreement. So the way to look at this is if your increasing speed, is your acceleration positive or negative? Take a look at it. See if you can figure... The A is positive, right? So if A is positive, is that going to make this term bigger or smaller? So if A is a positive number, will this get bigger or smaller? Bigger. Good. So if this goes up, that's going to mean that the way to look... Oh, no, hold on. My pencil has failed me. So we're going to see that if this goes up, right, Fn becomes greater than mg because we're going to add something to mg. The elevator is speeding up, so the acceleration is increasing, right? And it says it's moving upward, which takes away any of the ambiguity at increasing speed. If you're moving upward at increasing speed, you must be increasing. You can't just invent new motion. No, yeah, it says you have to. You are making up your own rule, Nina. Fn. Let's look at what the problem says, because the problem gives us the rules of the system. So in part B, the elevator is moving upward at increasing speed. If the speed is increasing, it must be accelerating. If it's accelerating, AY must be positive, right? Because if we look here, we're just summing the forces. We're saying that this is positive. If there were a balance, it would be 0. Do you see it? We have our model. And our model says if we're moving up and increasing speed, that is a positive acceleration. If we add numbers here, we get a bigger number than just mg. In order to have a smaller number, we'd have to subtract something off. That means the acceleration would have to be negative. And we would also, n to be 0, we would have to have no contribution from ay. And that's just not the case. Yes. And that's given from, let me write it here. So if you look at here, the elevator is moving upward, right? And we're looking at part B. So at increasing speed. That means that as time goes on, v gets bigger. That means dv dt is positive, right? That means that a is positive. And if you add a positive number up here, right, but that's part A. I do not want to confuse part A with part B. We've done part A. So at constant speed, A is 0, and we have that it's equal to. So part B, it's at increasing speed. Okay? Okay, good. All right. So I hope everyone gets it, and indeed we can see here as well that it agrees with us. No problem. All right. So moving on. Frictional force or friction. Okay? So friction occurs when one object slides or attempts to slide over another. This word here, attempts, is very important. Because if you push on something heavy, like if I'm pushing on my desk right now and it's not moving, I'm still exerting a force on the desk, and the desk is pushing back on me. And this will actually create this "or" will create two types of friction. All right? One will be static friction if we're attempting to slide. The other will be kinetic friction if we actually slide. And this is directed along the surface opposite the direction of the intended motion. So if we're trying to push an object along to the right, the friction will form along to the left. Okay? All right. See if they define static. And I think we'll break static and kinetic friction down in the next chapter. All right. We will often use ropes with things. So let's see if we have a picture. Good. So we'll often have tension, right, in a rope that looks just like this. All right. You'll notice we have three different roles of tension or modes of tension, and they all look very similar. Let's go back to the definitions, though, before we try a checkpoint. So a tension is force used usually by a string or a rope or something like that. The cord pulls on the body with force T along the cord, and the cord is said to be under tension. The tension in the cord is T. So before we deal with this word vomit, let's look to and see what that means. So you'll notice here on the body, right? I want to use the pen for a minute. So the body is the block. Let's make a free body diagram. On the block, this is the only tension on our system. Okay? We see that the source of the tension is this hand over here, but we just look at the system we're looking at, which is this block. And you'll notice that once you get to the hand, the tension, you have to be taught to have tension. You can't have slack. So you have to be pulling. If you look, the tension is pulling on the block, right? But if you look at it from the perspective of the hand, the tension is going the other way. This is looking at a second system. You'll notice, though, that you can do this in a few ways. If you put this in with a pulley, the tension is still going on the block in the same direction, but now this other force, the hand, is going down and going in a different direction. And here you can do the pulley this way, and now you've changed the direction of the tension on the block by roping it over and not having it sit on the table, right? Now that's not here. So keep in mind that the tension is constant throughout the cord, all right? That is, as long as we have massless frictionless pulleys, our tensions will remain the same. When things start moving and sliding, things get complicated, and we'll make things complicated, but not until, May. Real May, not my messed up May. You can't push a rope. No, you can. The rope can pull you, and you can pull on the rope, but you can't. If you get rid of that slack, you're no longer under tension. So if we go back to our definition, that we have to think of these as the rules and assumptions for which you can have, say, a body is under tension. All right. So the body it's attached to the body and pulled taut. If it's not pulled taut, like tight, then it's not tension, and you have to deal with it differently. Right. No compressive strength. Weight, normal forces are gravitational. So weight is gravitational. Normal force is not gravitational. Weight is equal to Fg, and the sensation of weight is from the normal force. Friction and tension have their own agents. the tension comes from the rope, like what you pull on it. And tension has to do with the material. So these forces are all filed under what we would call mechanical forces. All right, and when you're looking at T1 and the tension on the block, no, those are not T1 and T2. Those are just T for right now. Basically, you have to have, you need more machinery to look at pulleys and things like that. You need torques. But right now, as long as the pulleys are frictionless and lighter than the systems we're looking at, much lighter, the tension, and in the simple example where there is no pulley, the tension is just the same throughout the rope. Okay, you'll notice the tension in the cord is T. That's the last one here. All right, and these are all examples of what we call mechanical forces. So T is just, the tension in the cord is just T. Okay, when you apply it to a certain body, like when we go towards here, when we apply it to a certain body, so for instance, the tension on the block is pointing to the right, whereas in the hand, the tension is pointing to the left. Okay, but the rope is under tension and has a tension. You wouldn't call these T1 and T2, and you wouldn't call these T1 and T2, nor these T1 and T2, as long as we just have a simple pulley machine. If the pulley is thick and has a mass that's appreciable to the block, things can change, because you'll have a torque that you have to consider in this as well, and other forces to consider. But right now, if we ignore the effects of the pulley, the tension remains constant. And while that might seem like we're making up stuff, that's actually not a bad approximation. If you're using like 500 grams, which we would do in the lab, and the string were light, and the pulley was, say, 2 grams. We can do that. And if the pulley has very little, a nice slip wheel on it, and doesn't slip at all, or has nice bearings in it, and just is very smooth in its rotation, it's a pretty good approximation. But for Chapter 5 and Chapter 6, this will be true. I just want you to be aware that it does get more complicated, but it isn't yet. And you can only make things more complicated when you understand the assumptions that go into making a problem more complicated. That's important to know, because what we're using math is the way we check stuff and execute what we do, but really what we're learning how to do is manage our approximations, right? Really all the problems you solve are about knowing what applies and what doesn't apply, and being able to think about your way through it to create the simplest mathematical model possible. And then the solving is just what you do at the end, right? The math isn't really what's important here. It's setting up the math and knowing what assumptions apply and which ones don't apply. So when we're talking about simple tensions and ignoring the masses of pulleys and things like that, you'll often see that massless, frictionless pulleys, these tensions are, the pulley system looks like this system with the hand, where the tension is just the same throughout. Okay? I know that seems like a lot of words, and they were repetitive, but I hope it makes sense. But let's go back and make sure we've covered everything about tension. So, the massless and unstretchable cord exists only as a connection between two bodies. All right? It pulls on both with the same force, this is the tension, and this is true even if the bodies and cord are accelerating, and even if the cord runs around a massless, frictionless pulley. Now remember what I said, massless, frictionless pulley. These are useful simplifying assumptions. All right, so you'll notice on the bottom here of the slide, they really do talk about what I was saying about managing your assumptions. And you have to be cognizant of these assumptions. These are the important parts. So under these assumptions, we can treat the tension as, again, the same throughout the string. However, we have two bodies in each problem. We have the block and the hand, block, hand, block, hand, and we can see the tension in its different directions in each of these setups. Okay? So now we want to concentrate on this picture. And this picture will help us with our checkpoint. So the suspended body here in in the circled picture weighs 75 newtons. And we want to know, is T equal to, greater than, or less than 75 newtons when the body is A, moving upward at constant speed, B, at increasing speed, and C, at decreasing speed. So, if we look here, I'll do part A with you. So the way to do this, formally, if you're looking, how do I do it, is say, well, the sum of the forces. Well, first let's make a free body diagram, right? So we'll do that here off to the side. We have T going up, because we're looking at the block. Okay, so we have T going up. We have, that's supposed to be straight down. That's bothering me though. I can't go on. I can't go on. And we have mg straight down. Now, when we sum the forces in the y direction, this will be equal to the tension, right, because it's going up, minus mg. And this will always equal may, right? So now we can look at it. Oh, we've already got one reported in. So in the first one, in A, ay will equal 0. So therefore, we have equal to, right? Because ay goes to 0, t is just equal to mg. Now, for B and C, try them on your own. Mina's already reported an answer, which looks pretty good to me, but you want to be sure you can understand it. So I want to give you a minute. I will get some water. I need some more water, so while I do that, see if you agree with Mina's conclusions. Remember, it's important to understand why. If you don't understand why, you should ask me a question. I will go over it, though. Yeah. Hold on. Okay, I'm back. Good. It looks like everyone's getting on the same page there. Hold on. Jesus. So, if we look here, with increasing speed, right, we can see that much like we saw before, T is equal to mg plus may, right? So if may is getting bigger, right? Oh, the camera's still off? All right. Hold on. Sorry. The breathing is taking priority. And that's not going well. So if we look here, right, at increasing speed, ay is increasing. So we should get B to be greater than. And if we look here at decreasing speed, A will be negative. So this will be mg minus some number. mg minus some number. And C will be less than. All right, less than 75 newtons. Okay? So I think everyone got that. As we can see, that's the cleaner version. You can see it in nice typeset. It's very nice there. All right. So now applying Newton's laws. So now we get to my favorite law, the third law. And we can introduce it, but then this will probably be, we probably won't get to any examples on it because it is 3, so we only have 15 minutes left. I already took my picture attendance, so we should be okay there. Newton's third law. So when two bodies interact, the forces on the bodies from each other are always equal in magnitude and opposite in direction. Basically, more popularly, this one is described as for every action, there's an equal and opposite reaction. Action movies love to quote this one and tell you, oh, well, you know, if I do this, then this thing happens. But when in reality, what Newton's third law does is it connects two bodies. So if we have two objects, right, that are exerting a force on each other, let's say it's two blocks pushing on each other. This is block A and block B, A and B. They exert equal and opposite forces on each other. We can only analyze one body at one time. So a way to think about this is if you're in a fight and you get hit in the face, the equal and opposite reaction is you not hitting them back, it's your face hitting the fist. So there's action, fist hits face, reaction is on the face hitting the fist. So it is physically correct to argue that you didn't hit someone, their face just ran into your fist. However, legally, you're not going to get very far there. But why Newton's third law is my favorite is because, for a few reasons. One, it connects multiple bodies. So if we have a system of many particles or many things, it dictates or it provides the rules and structure for interaction. And one interesting thing I like to think about, so I enjoy shows like Supernatural and, you know, horror movies and things like that. And it's always the ghost can go and like punch you and beat you up, but you can't touch the ghost because it's a ghost. And what Newton's third law really specifically says that you can't act on something without being able to act on it, right? So that's an interesting, and I've always found that interesting where movies get away with that, and they can because movies are supposed to be fun. They're not supposed to be physically, you know, take place in the physical world, but it's one of those strong reasons for thinking about the supernatural. No, not quantum entanglement. This is all classical stuff. Basically, and quantum entanglement quantum physics does not really violate Newton's laws in that sense. Newton's laws are continuous. Quantum physics is discrete. But energy has to be exchanged in quantum physics. Even in entanglement, there's energy associated with it, and energy conservation is not violated. So you can look at all interactions energetically too, as applying an interaction energy to an interaction. Now you can have energy go through in ways that are not classical for sure. That happens, but only at the atomic level, and specifically even quantum mechanics says that at the human scale, at our macro scale, you can't have those interactions, or at least you're very unlikely to have those interactions. So the ghost can affect you only once, at least, in the existence of the universe. Multiple hacks are very unlikely, are not expected. It wouldn't be an ability. So yeah. Oh, okay, good. That's all coming. Camera's back on. So essentially, it's a fun place to think about that, and I always sort of use that as a guideline when people are like, oh well, this thing came in and I couldn't interact with it. It's like, well, you don't have to worry about it affecting you if you can't affect it. But getting back to our lecture here between two objects, when forces act from one body to another, you'll notice if we have two bodies, we would need two diagrams. So that's the diagram for A, that's the diagram for B. So if A pushes on B, right, then B will push on A. Here they call it B and C. That's unfortunate. But you can see that the magnitudes of these forces will be the same as illustrated here in this equation. And the directions, vectorally, you'll notice that they're equal and opposite. Now, we call these two forces, see right here in the vector, FBC equals minus FCB. You'll notice that when you look at the drawing, they are indeed equal and opposite. So these are a third law force pair. And notice this is important. Anytime two objects interact, there is a third law force pair. So keep that in mind. But also, I want to point out, I want to go back just for a little bit, and I want to point something out. I want you to notice that these are not a third law force. These are two equal and opposite forces that happen to act on a single body, but in order for Newton's third law to come into play, you need to have a second body. So you need to have a free body diagram for the block, which we have, and a free body diagram for the table, and then look at the forces separately on the table, like over here. I'm not going to do that because we have more things to get through, but I want to point that out, that in order to use Newton's third law, you need two bodies. It's about interaction, not just forces being equal and opposite. Okay? It's fundamentally about interaction. So keep that in mind, and don't get confused by that one. All right. Let's see what else Newton's third law has for us. So as you can see, we have, if we look at gravitational pairs, if we're looking at something like the block sitting on a table, right, we can look here at the, or we're looking for the equal and opposite force for gravity. It's not the normal force back on the table. In fact, the right way to look at it at a correct pair is the cantaloupe falling towards Earth and the Earth. And here, they're basically making my point. Here, the cantaloupe resting on the table, you'll notice they're just analyzing the cantaloupe. You could analyze the table and make a cantaloupe table pair, but that's not what they're doing here. All right? These forces just happen to balance. Here, you have a third law pair. You have two objects, right? You have the cantaloupe and you have the Earth. Now, I want you to notice something. When you look here at this here, you have two objects. You have the cantaloupe, and now you'll notice that they're not looking. Here you have the normal force is CT here, but here it's not the gravitational force. You have the force pushing up, and then you have, this is the force of the cantaloupe on the table. It's not the gravitational force. So that's what makes these a third law pairs. You're looking at the interaction between the cantaloupe and the floor. And that's what makes this a third law pair. But here, so you'll notice that there's two bodies here, there's two bodies here, there's one body here. Okay? So, let's see what else is in store for us. So, I think a checkpoint cliffhanger is probably a good way to end. So, suppose that the cantaloupe and the table are in an outer cab that begins to accelerate upward. Of course, we're always doing these apparent weight things. We don't do apparent weight. Do the magnitudes of FTC and FCT increase, decrease, or stay the same? Okay, that's a big A. B, are those two forces still equal in magnitude and opposite in direction? And C, do the magnitudes of FCE and FEC increase, decrease, or stay? Wow, there's a lot here. And D, are those two forces still equal in magnitude and opposite in direction? So this will be our great checkpoint cliffhanger. We will go over this one. We'll start. This is a great place to stop because it'll let us go over pretty much everything in the first time. So when we get the answer, I'm not getting it away this time. So I want to go over it as a review to get us going next time when we start expanding into forces and doing problems. Okay. So I've taken attendance, and does anyone have any questions? Can you go to the previous slide for a second? Sure, I can go to the previous slide. Yeah, so study that one all you want and take a look. We'll use that, go back to this as our final slide, and we'll pick up the checkpoint tomorrow, or not tomorrow, but Thursday. You will have a lab on Tuesday that will be uploaded. I have to get that done over the weekend, and I do want you to know that you will be doing. It'll basically be 2 to 3 weeks worth of lab. Lab 2, I think I have lab 2 due. Check on Blackboard. I think I have it due Friday, if I'm not mistaken, but it might be due Wednesday. Get it done. Don't let it linger. But yeah, lab 2 is due. Then if you have questions, Wednesday, April 1st, then that's what it is. It should be really easy to do. Don't let it linger. But what I'm going to do is for lab, I'm going to make, we're going to do simulations, but we're not going to, there's not a good one-to-one comparison, but there's a good subject sort of comparison. So basically we're going to do a lab, our next couple labs, we're going to do a projectile motion lab next week because we've already done that, so I feel good about doing that. I'm going to skip the vector force table bit. So we'll do a projectile motion simulation. So that will actually be one lab. And then we're going to do, if it says April 8th, then it's April 8th. Homework 2 should not be due. I'll have to change that date. I just haven't changed the date on the homeworks yet. So I got to do that. But basically, the labs, we're going to do like a set of 3 force labs. So we'll do a long form lab report. We're going to have more long form lab reports that I promised you. So we're going to do a long form lab report on forces, and we're going to do a long form lab report on conservation laws, and then we'll have, and I think that we'll see how many simulations that covers, because I think that might cover, each one of those might cover 3 to 4 weeks of lab. So you'll be playing with it a lot, and the questions, the instructions will all be verbal on the video that you'll see. So you'll be able to watch and rewatch it at your leisure. Okay? So that's basically how lab should work. Like I said, lab is hands-on. I'm more than happy to answer questions about lab, but I feel like you can do lab at just about any time virtually, and I can answer those questions anytime virtually. So we don't meet like this for lab, just to make that very clear. Okay? All right. Well, so the only short reports will be 1, 2, and 3 will actually be short form reports because we're going to do projectile motion. Okay? All right. Well, have a good weekend, everybody. I'm going to stop recording.